Hello, my name is Henrik Sandberg and I'm here to present the project ROSE, Learning and Routing Games for Sustainable Electromobility. And I'm a professor in Decision and Control Systems at KTH. This is the team in the project. We have Professor Saurabh Amin from MIT, and we have Professor Stuart Stan and Gyoso Ginufalvi at KTH. And then we have former postdoc Hanpei Sasahara, who is now an assistant professor at the Tokyo Institute of Technology. The goal of this project is to look into traffic routing for commercial logistical operators and to look more into sustainability issues related to the routing of vehicles and goods that are sharing both electromobility and internal combustion engine vehicles. The project has three pillars. First, we look into simulation of the traffic infrastructure and the traffic flows to quantify costs and pollutions. We look into optimization, trying to find the optimal routes. And third, we look into the game theoretical aspects, so basically the competition between the different operators sharing the same road and charging infrastructure. And this is what I will focus on in this presentation. Here you see the model setup we're looking at. It's a simplified model so that it's more tractable for mathematical analysis. So consider a case where we have a single origin, so say Stockholm, and a single destination. Think about Gothenburg, for instance. And there's multiple routes between these cities, and each operator, commercial operator, say there are N of them, capital N, they have a fleet of internal combustion engine vehicles and electrical vehicles. And they have a choice now to put the goods on either type of vehicle and also which route to use. Each operator needs to deliver capital D, N goods. So basically every operator has a decision to make how much goods to put on each type of vehicle and which route to choose. This is what is called an N-player atomic routing game. The cost functions that we're looking into is capturing two aspects of this. So there is what we call a delay cost. So if the goods is being put on electrical vehicles, we assume the routes are long enough that it will require some recharging of the vehicles on the way. And if there's a lot of traffic on a particular route, the charging infrastructure may be congested, and that could cause delays on that route. And delayed delivery will cause a cost. That is item number one. Item number two is that if you instead put the goods on an internal combustion engine vehicle, there we assume that there's a tax on the use of polluting vehicles. So basically there's a cost proportional to the amount of goods put on that type of vehicle. Mathematically, this is being modeled as follows. Essentially, every operator has chosen a profile on the amount of goods to put on each traffic type and route. Each operator has a cost function, Jn, which separates into the different routes and traffic types. And there's this pollution cost as well. And we also assume that this delay cost is a convex function of this type, and up to a threshold there is no delay cost because the particular route can carry this much traffic without causing congestion. But as soon as a lot of traffic is put on this route, it will pass this threshold. Essentially, it will start to cause delays on the road, which will incur costs. The so-called green routing game we define, which I also presented last year, then we look for solutions where each operator is trying to optimize his or her own cost function, Jn, and they will be satisfied if they find a Nash equilibria. Essentially, they have found a traffic profile so that there are nobody in this, no operator has any reason to deviate from this strategy. Then we call this a Nash equilibria. And last year we showed that these equilibria exist, and they are essentially unique if the delay costs for every operator is identical. if the delay costs are different for different operators, we also show that there actually are several different type of Nash equilibria. So what has happened since last year is that we've been looking into the inefficiency of these Nash equilibria. So the Nash equilibria essentially models the outcome when these operators play against each other in a selfish manner. So to see how inefficient this can be, we have looked into the social cost. The social cost we define as the total cost of all the operators together. And then we introduce the so-called price of anarchy, which is the ratio between the worst outcome of these selfish operators versus the outcome of a optimal planner, so a global societal planner decides the routes. And you see the difference between the total outcome here. And some examples we are looking at are the following. So here you look at the simple case where we have two operators and we have identical delay costs, so we know that there are essentially unique Nash equilibria, but the pollution costs are different for the different operators. And we have a scaling parameter C here, so we can change the marginal cost of the pollution tax. One observation is that as you increase the marginal cost, so the parameter C, the price of anarchy tends to decrease to zero, although we don't have any proof of that for now. It essentially means that when the cost of the pollution tax is very high, the selfish operators more or less will converge towards the global optimum, namely the global societal optimum. Here, for instance, you can see the use of the internal combustion engine vehicle as a function of this marginal pollution cost. And you can see that when the marginal cost on the pollution is around 8, none of the selfish players will use any pollution ICEV anymore. We can also see from our studies that the total societal cost will increase with this marginal pollution cost. So somehow one would like to think about in the future maybe how to redistribute this collected environmental tax back to the operators to incentivize a correct behavior, so to say. Another extension since last year is the green routing games with incomplete information. So here we have introduced a network state S, which is uncertain in general. So basically this state could model that the operators, when they do the planning of how to route their goods, they don't know perfectly about the road conditions and the costs and the availability of green power, etc. But we do assume that there is some sort of public information system that is providing all of the operators with some sort of probabilistic belief about the state. So when they do the planning, they have some sort of guess information about what's the most likely state of the system, but they all have the same belief about the network. Once the game is being played, the actual system will have one particular state, S star, of course, but this may or may not be known at the time of planning. In this framework, we instead need to look at another concept, namely the Bayesian Nash equilibria, which are kind of similar to the Nash equilibria, except now it's being parameterized of the belief. And in this case, basically it means that no player has any incentive to change their planning under the common belief. Then we have found a Bayesian Nash equilibria. And in our follow-up work, we've shown that much similar to the previous work, that also the Bayesian Nash equilibria are essentially unique if the delay costs are identical. We've been looking into the social costs, which now are parameterized by now by the state. And an interesting concept to look into now is what is called the value of information, which is now the difference of the social cost when the players are planning with their common belief versus the social cost if they had known the state perfectly. So what is the difference between these two social outcomes? If this is positive, it basically means that it's good for society to provide a better information to the planners. They would actually, the social welfare will be better. So what can we then say about the value of this information? Well, we actually have somewhat counterintuitively found examples where it can be negative. So essentially saying that providing the operators more information, that they have better information, that actually can be negative in terms of the total societal welfare. Here is one particular example with two operators with identical delay costs and two different states of the system, S1 and S2, where the system happens to be in state S2. Here are some particular numbers for the pollution costs. It's not so important what they are, but just indicate here that here is the outcome of the social cost when the operators has perfect information about the state, and here's the total cost when they have uncertain state. And here you can see that they actually do better when they have uncertainty. Although we have also identified cases where it's positive. So for instance, if the demands, delay, and the pollution costs are identical, then we can prove that the value of information is actually non-negative. Here's the same example again, but now the pollution costs are identical for both players, which they were not here, and then indeed the value of information is positive. So to summarize, we've been looking at the competing logistical operators sharing a road and charging infrastructure. We've been looking at the trade-off between these two traffic types and the concepts of price of anarchy and the value of information. Into the future, we are looking into more how to internalize these congestion and environmental costs into the planning phase, and we'll also look a little bit more into the price of anarchy. And with that, I would like to thank you for your attention.